We now talk about a dipole in a uniform magnetic field. So we saw in the previous chapter that the torque on a loop placed in the magnetic field was given as, so the torque was given as I times the area vector cross product with the magnetic field. So we denote this by mu vector called the magnetic moment. So torque now is, the torque vector is cross product of mu vector with the magnetic field. So the magnitude of torque is given as mu b sine theta. Now this angle theta, this is the angle between the area vector and the magnetic field. So you know the area vector is nothing but normal to the area. So let us see this in the diagram. So say this is a current carrying loop. So the area vector goes like this. Recall that if you are given an area like this area is A, then the area vector is normal to this, that is perpendicular, and the magnitude of the area vector is just A. So this area vector makes an angle theta with the magnetic field. Now this is difficult to see, so you just see the bottom side now. So we are taking this bottom side. So the view from the bottom is like this. So you have the magnetic field, the area is perpendicular to the area of the loop. This is the area vector, it makes an angle theta. So notice this red dot, this means the current is coming at you. This you can see from here. If you are having a look at the bottom, you see the current is coming at you, and this is the current going away from you. So this side is current going away from you. So this is the angle theta. Now work done in moving the loop. So we had seen that the net force on the loop was 0, but the force was acting at two different points, so it produces a torque. So the small amount of work done, dW, is nothing but torque times d theta. So the small work done gets stored as the potential energy. So integrating this, you get the potential energy, which is stored as the work done. So U is the potential energy. You put it equal to integral of torque d theta. You get mu b sine theta d theta. This is a constant. This is independent of theta. So you take it out and recall that integral of sine theta d theta is just minus cos theta. So this is how you get minus mu b cos theta, and you rewrite it as a dot product of the magnetic moment dot product with the magnetic field. So we see that the system has the least potential energy minus mu b at theta equals to 0. So you plug in theta equals to 0, you get minus mu b. So this is how theta equals to 0 looks like. The magnetic field and the area vector are in the same direction. Notice that you have a dot here and a cross here. Dot means the current is coming out of the screen at you, and cross means current is going inside, just like in the case above. Now the maximum potential energy is at theta equals to pi radians or 180 degrees. At theta equals to pi radians, cos of 180 degrees or cos of pi is minus 1. So this becomes mu times b, so which we have written right here. So this is when the area vector points in the direction opposite to the magnetic field. Now these two figures look exactly the same, then how is this area vector pointing in this direction? So notice that what we are going to do is we are going to put a cross here and a dot here. So this is the opposite direction. So current is coming out of the screen here and going in here. Here the current is coming out of the screen here and going in here. So this is the maximum potential energy, and this is the minimum potential energy.